Okay, so I'm just picking up some random problems for us to work on. So number one here, definite integral from 0 to 2, x over squared 1 plus x squared. We know that the bounds is not going to play a role at the beginning, so I'm just going to ignore the bounds and just pretend like my problem doesn't have those bounds. And just focus on what I see with the indefinite integral. Right? The thing that we always ask ourselves is, can I just expand this through and rely on power rule? No. What's the issue? Okay. There's more than one term in the denominator, and also the square root we can't bring up. Okay, just too messy inside the square root, multiple terms preventing us from going further. So let's rewrite the problem to help us see our potential u value. How can we rewrite the problem?
1 plus 2x squared to the 1.
Okay, so things should become more clear. What's our u value?
Plus 2x.
Yeah, so once you get a set of parentheses, your u value is what's going to be inside the parentheses and not including the exponent outside.
Mr. Yang, is it fine to bring the 1 plus 2x squared up and put it as negative 1/2?
Yes. We know eventually it's going to have to come up. I'm going to wait till later, but if you do it now, no issues there. Okay. But yes, that's a good point. We ultimately, this is going to turn into a power rule problem, and this u has to be up top before we can go through a power rule. Okay, our u value is 1 plus 2x squared. We'll do some cleanup here. Or find the derivative first, sorry. U dx equals cross multiply. Okay, dx equals right. I'm just going to substitute what I've underlined, but everything else I'm just going to recopy over. Right. The important thing that we have to resolve is, are the x's going to go away nicely?
Yes.
Yes, that's a good sign. That means we can move forward, get it ready for power rule. So how would you get this ready for power rule? 1/4 out. What else?
Bring the u to the top.
Yeah, we can't leave this u to the bottom and go through power rule here. It's not going to give us the right answer. The variable has to be sitting nicely up top. Okay, we're ready for power rule. U to the negative 1/2 becomes okay, everybody good with this? Okay, I'll flip that 1/2 up as 2 over 4. Is 1/2. All right, we have our antiderivative. We put a plus c here. No, because ultimately we're going to work in the bounds. We're going to get a numeric value. So we got to make sure that we're not making a mistake with the bounds. Okay, we don't want to involve 0 and 2 with this, as tempting as it is. I see a lot of students do that, but that's a mismatch, right? You got variable u sitting here, but these are variable. These are in terms of x. So what a lot of students prefer is bring the u back in terms of x. And then once in terms of x, then the bounds you can use without any issue. Okay, upper bound first. Minus lower bound. Oh, careful. I think a lot of students do this. They see the 0 and they assume that it's going to wipe everything out, but just be careful, right? Sometimes that's not always the case. Zeros usually does clean the problem expression up a little bit, but it may not wipe everything out. It doesn't wipe everything out, right? There's still that one left over. So what's 9 to the 1/2? Right, square root of 9 is 3, so 3/2 minus 1/2 is equal to 2/2, which is equal to 1. The other option, which you don't have to do if you don't want to, but I want to show you, is we can use this 1/2 u to the 1/2 and then just work the bounds in terms of u and then work it from that perspective. And now that my bounds are also in terms of u, same answer, slightly different method. Okay. Anything specific you want to do, or you want me to just pick out problems? Okay. All right, let me create one. Second. It's gonna work out. Mm. Sorry, I'm gonna do this second. Okay, so where do we start?
Going for a
Okay, so which one, first or second one?
second.
Second, because that's a shorter interval, right? But this is a short interval, but is there something that we can do to make it a little bit clear? This is not very clear here. Because,
Flip it.
yeah, because this is going backwards, right? Going backwards is a little bit weird. So if I rearrange that, that's really the same thing as what? From 4 to 7 of f of x dx equals -3. I hope this works out and work this out all the way. Okay, so let's sketch that out from 4 to 7. So if I know this piece is -3, what else do I know? It's even here.
The same on the other side.
That's
Side. All right, so these are sets, okay? I'm not going to create any overlap with these two. This is not going to change. Now let's go to the larger interval here from -4 to 7. We want this whole thing to add up to be what? -5. Okay, we already have -3 here, so what else remains? -3 and what will give me, yeah, so -2, and I gotta split -2 evenly. So this is -1 and -1. Does that make sense? Are you guys okay with that? So now that you have the graph in front of you, now I can figure out what is -7 to 0 going to be. What's from -7 to 0? What are the areas added together? -4. Okay, odd function doesn't quite work with this example. Do you guys need to see an odd property? Create another scenario here. Oops, sorry. Sorry. No, I need to think about how I create this mirror. Okay, let me redraw this again. Sorry. Okay, so we start with a shorter interval, 4 to 2, but what's weird about this shorter interval here? Yeah, it's not in order, right? So let me make it easier for us to graph. I'll go from 2 to 4 is -3. Okay, so we start with that graph. So 2 to 4 is -3. What do we know about the other side? Is what? But it's odd though. Mhm. -4 to 2 is equal to -2. So I have 3 here already. What's the missing piece that will get me to -2? Three, and what will give me -2? So I need -5 here. No, I can't do that, can I? Odd. This has got to be split. Sorry, I did not create this problem correct, because if this is not a good scenario, because these have to be opposites, right?
Yeah.
Okay. So maybe an adjustment I can make is, let's say instead of -4 to 2, I say -4 to 0. So from -4 to 0, it's going to total to be -2. So this must be what? -5. And if this is -5, then this must be a +5. Okay, so that's better. So now to find the integral from 4 to -2, this is backwards here. 4 to -2. I want to flip this, make it from -2 to 4 with a negative in front. So -2 to 4 is really equal to what? Yeah, -3 with a negative, so it's gonna be a +3. Sorry about all the changes. But the big picture is start with a smaller interval. build out the other side using either even or odd properties, and then finally use the overlap information to help you fill in the missing gaps. All the meanwhile, keeping in mind that your odd functions will always zero out as long as you're looking at the same distance from the origin. And then your even functions will always be mirror images on both sides of the y-axis. Okay.
One class, can you go over like the theories of calculus one more time?
You mean the second theorem?
Yeah.
Yeah. Yeah. So basically, the second theorem, you're just going to follow the rule and take turns with the upper and lower bound. So just to show you real quick here. Number 7, if I want to find the derivative of this region, I know that derivative integral will just wipe each other out. I just have to worry about my upper and lower bounds. So plug the upper bound into the expression, just a straight and substitution. Okay, so normally we don't do this, right? We can't do this if it's an integral problem, but it's a derivative of an integral. That's why we're able to just plug the upper and lower bounds in. So upper bound into the expression, multiplied by the upper bound's derivative, minus the lower bound into the expression times lower bound's derivative.
Okay.
Yeah.
Thanks.
I'm not going to be so worried about the cleanup. If you can get to all the parts here, that's the majority of things. Yeah.
You got a new clock?
I took the one from the back because this is the old one was just not accurate.
I have another one.
I moved that one up. Say Jack.
Because you have to do it 2 times, correct? Because there's 2 variables.
That's right.
So are you gonna minus them like you did the other ones, like minus big parentheses and then?
That's right. Minus big parentheses and then the lower bound.
Okay.
Number 7.
Yeah.
Okay. So then it says find the derivative of this. So basically we're trying to do this here. Derivative. So there's something special that we can do if you're doing 2 opposite operations on the same expression. So if the upper and lower bounds are both variables, we're going to follow this rule here. And this rule is f of p of x times p prime minus f of q of x times q prime. What that means is I'm going to take this upper bound, insert it into the variable of the expression. That's my f of p of x, multiplied by the upper bound's derivative, minus big parentheses, f of q of x times q prime. So I'm going to insert the 2x cubed into the expression variable multiplied by the lower bound's derivative. Right? So root x into the radical That's the first part. That's my f of p of x. Multiply by p prime. So how do I find the derivative of square root of x? Mhm. Yeah. So that completes the portion for the upper bound. Minus. Lower bound also is going to have a remnant that remains because this is a variable. So same process. Plug 2x cubed into the variable of the expression. Times the lower bound's derivative. 2x cubed becomes 6x squared.
With the square root and the square, like the first one, or cancel out. Or like maybe.
Yeah, so the square root of x squared is just the same thing as x to the 1/2 times 2, which is x to the 1. Because square root of x is same thing as x to the 1/2. So what's 1/2 times 2?
This one.
1.
Okay.
So that's why it disappears. Theorem.
Theorem when it's like you're taking the derivative.
That's right, yeah. So it has to have this particular notation. If it was just this integral, we have to go through a power rule and all that, but because these two are next to each other, we do something special because of the fact that we have two different things acting on the same expression.
Okay, but then there's the dt and the inside too. What is that?
Oh, what happens to this dt, you mean? So imagine you take the antiderivative. The antiderivative is going to produce, or sorry, you take the integral. If you take the integral, the dt disappears. And then whatever that result is, you find the derivative of that, and this is going to be a bunch of expressions and numbers. So it's just like this, right? The dt disappears because imagine I asked you to find the integral of x squared dx, right? That's just become x cubed over 3.
Yeah.
The dx goes away. So now imagine.
Just say take the antiderivative. Or is it?
Let's see. So your question is, why does the dt disappear? Or what's your question? So I'm just following what this rule says, right? The rule allows the integral in dt to go away. All I need to worry about is the upper bound into the original function times the upper bound's derivative minus lower bound's derivative times lower bound's derivative. If you want to see a full worked out problem to see why that dt is not there, I can do that if you want to see it.
Okay. Like 4 efficiency.
This one here, number 4.
Yeah.
So this one, we got to go through the full u substitution, right? We don't do this special process unless a derivative is in front of a derivative integral. So do you need to see the steps for number 4?
Try to solve it on my own.
Yeah.
When does DT sitting the same DX as well?
Yeah, dt is dt and dx are the same thing. It's just that dx tells you is declaring that x is the independent variable. dt is declaring that t is the independent variable. So
Usually when there's both parentheses, is that usually like gonna be your U value?
yeah, if you see a set of parentheses, usually that's going to be a u value. But you always want to look at the problem and see, is it possible to expand it without u substitution?
Yeah.
Right. If you hit a roadblock there, then you want to think about u substitution.
So, on the floor,
Mm-hmm.
when you get to the step where it's like the, like the 1, 2, 3, like the fifth step, the 5, 6,
Mm-hmm.
inside of the secant,
Mm-hmm.
why would you, or would you wanna plug the U in there?
No, not until you take care of this rule. So let me box off what we want to recognize here. Do you recognize that integral of secant squared u du?
Yeah.
So we want to apply the rule that's associated with that. So the rule for integral of secant squared u du, you can look on the formula sheet here. It transforms into tangent of u plus c.
Okay.
So after we make that transformation and we're basically sitting at the answer, then we can bring the original variable back. But we want to hold on to that u value to help us recognize the rule so we can apply the rule. And then at the very end, we can bring the x back in.
For number 6, why would you choose U substitution again?
For number,
On that same page.
oh, you mean this piece right here?
Yeah.
That's not u substitution, that's the converting the bounds to plug in.
No, but like you overall you have to use U substitution, don't you?
Number 6, yeah,
Yeah.
you do.
Is fine.
Because I can't expand this. I mean, I could, but
It's
it would
gonna
take
take
too
long.
long. It'd take longer, right? So anything that's higher than exponent 2, I want to consider u substitution.
Okay. You over absolute value.
Mhm.
That we get up.
So. Number 10. Or let me, yeah, let me create a new one. So we're gonna sketch the graph. Extend the graph out so it looks like a V. And then extend the V out as far as your left and right bound. Okay, so where's the graph gonna live? Where's the vertex? Where's the V gonna? At 2, yeah. Oops, sorry. -3 to 7. I did not spell my graph correct. Okay, plug -3 into the function. -3 minus 2 is -5. The absolute value of -5 is 5.
We're just playing with the epsilon for.
Plug x value into the function. Plug 7 in for x. What's the y value? Now I see 2 triangles. Can you find the width and height of each triangle?
-15. Wait, are both faces small?
Yeah, they both have the same dimension. Mhm.
Are you done with that? Wait, remember?
Yeah, let me just finish this here. 1/2 base times height. Plus 1/2 base times height.
Will they always have the same dimension or like the same?
Yeah, the way that I'm gonna get the problem, your width and height is gonna be the same. But the two triangles may not have the same dimensions.
Okay.
So on this problem, I'm getting confused because I get like a lot.
Yeah, and you're not gonna get x to go away, right? Is that what you're wondering?
Mhm.
So we have to go through another step to get us there. So you try to expand, you can't expand, you're stuck, you gotta go through U substitution, right? You rewrite it using parentheses. Derivative is -1. Okay, so we make our substitutions. All right, so what's the issue? What's preventing us from moving forward? The X, right? The X doesn't cancel out. I see some students, they do this, they want to do power rule twice, once for the X and once for the U, but we can't do that. That multiplication is preventing us. So we have to find the X's aren't canceling out, so we have to find a way to get the X to be replaced with something else. So the hint is, can I get that X to be in terms of U, and how can this help me out? Solve for X. X equals. So I'll move the X to the left side and I'll move the U to the right side.
Oh.
So X equals 7 minus U. So this is now going to substitute this. Okay, I'm still not in the clear, but at least I'm moving towards what that needs to happen, right? I got to get the X's to go away, and then I'm going to try to expand, clean up, and see if I can eventually get it to the point where I can just rely on power rule. Okay, FOIL out your 7 minus U squared. So 7 minus U times 7 minus U is 49 minus 14U plus U squared. And then you're almost there. Distribute the negative U to the 1/2 through. Then all the parentheses are gone, and then you can do power rule. U to the 1/2.
Square come from when 7 minus U.
The square here?
Yeah.
Is coming from the X squared.
Oh.
Right, so I replaced the X, but the squared is still there.
Can you go over average value there with the graph and without a graph?
Mm-hmm.
And go page 7.
So on page 16, this is average value with a graph. So or page 14, but I'm looking at 16 because of the key. So we know average value theorem, 1 over B minus A. from A to B of f of x. So I can replace my A and B with -2 and 5. That's not an issue. So I get to this point here, right?
Yeah.
So now I got to figure out, how do I replace this? Well, I have all these geometric shapes in front of me. I can just add up those areas and replace that with with that notation.
Oh,
So I'm looking at my region here from -2 to 5. Triangle, square, triangle, semicircle, triangle, square. I'm going to find the areas of each, add them up, make sure that anything below the x-axis I want to keep as a negative value. And if you see a semicircle, I'll give you that formula. It's 1/2 pi r squared. And then once I can add up all those values, clean it up, I get 7 minus pi. And then I have my width component and my height, so my area component. So it's basically area divided by the width equals the average value or the height.
so you're just adding up the areas first and
Mhm.
plugging them into,
And then I plugged it into here and then I made sure I kept that 1/7 in front.
and then you build up.
Yeah, multiply that through. Yeah.
Okay.
And then average value without a graph, then actually average value, like number 2 on page 19. You're just going to go through power rule instead.
You're gonna find that area first.
Well, if there's no graph in front of you, then you're just going to rely on power rule to get you there.
The area, right?
That's right. Antiderivative is the area. So either if I give you if I just tell you f of x, I got to give you the graph.
Okay.
If I give you a function, then I expect you to work it out using power rule. Yeah, using antiderivative. Mm-hmm.
Like on like number 12. Once you set up like the width and everything, like how do you know what the next step is?
Are you talking about this number 12? This one here. So the integral from a to b of f of x, that's the area, right? So I have this graph in front of me, so I can just do the area, add up the area using geometric shapes. Just have to keep in mind. That's right. Yeah. But just keep in mind that the portion below the x-axis need to be adjusted with a negative value.
Okay. And this graph is of x of the.
Because they say the graph of f is below.
Okay.
So they're giving you the graph, and the graph is just, it's this here. It's just a bunch of piecewise functions linked together.
The graph, once you find your antiderivative, what do you do?
And then you plug in the upper and lower bounds.
and then
get the
it's like
area.
minus.
That's right. Yeah, upper bound minus lower bound. And then once you get that area component, don't forget about that width component, multiply by the width, or divide by the width, and that's your
Okay.
average value.
And then from that, when you get your average value like 8/3, where does that go? In the original? Sure.
Let's see.
On page 19.
Oh, page 20, you mean? Or don't have to. That's right, yep. So once you have your average value, that's your Y value. Insert that Y value in for the Y and solve for X.
Okay.
Yeah.
Is it okay if we were, is there square root form? Do we have to like?
That's fine, yeah. You don't have to leave your answer
It's
simplified.
only the positive one, right?
Just the positive because, that's right, we're going from 0 to 2, so just the positive.
So if it's outside, you know,
That's right. If it's outside, we don't keep it. If it's on the end point, you keep it. You do keep it.
only when it's like what for average value.
Yeah, only for average value, right?